All right, lots of fun stuff to learn about in geometry in Unit 2. It actually starts with just kind of some things you've been doing for a long, long time in your life. Take a look at this. What's the next figure? What would be the next figure in the following sequence? What would figure 4 be? Well, as you can see, we start with a full circle, we cut it in half, and we shade here. Then we cut it in half again, and we shade here. Then we cut it into sixth. So we went 1/2, 1/4, 1/6. Hopefully you got that the next one would be 1/8, and we would shade right here. Notice we're always shading with the bottom left, right? So it should be this one. Good, and then that would be 1/8. And what would the next one be? Notice the pattern, 1/2, 1/4, 1/6, 1/8. Now there's no reason why this has to be the next shape other than our best guess. We're not given a rule. We're not told what to do next. We're just observing what's happening and trying to figure out what's next. That is mathematical reasoning. That is called inductive reasoning. So first we come up with some kind of a conjecture. It's an unproven statement based on our observation. And coming up with that conjecture, that's what our answer was for figure 4. We're using inductive reasoning. That's when we look at specific cases and try to come up with a general idea. You can think of inductive reasoning as going from a specific to a general statement. Think of inductive reasoning as going from specific to general. We are observing a pattern and we're trying to come up with a general rule for that pattern. All right, let's try another example. Given 5 collinear points, make a conjecture about the number of ways to connect different pairs of points. The best way to start a problem like this is to build up. I've got 1 collinear point. How many ways can I connect those different pairs? 0, right? How about 2 collinear points? How many ways can I connect those points? Just 1 way. How about 3 collinear points? I've got 1, I've got 2, I've got 3, and I've got, I think that's it, right? 1, 2, 3. 4 collinear points. How many ways can I connect 4 collinear points? 1, 2, 3, 4, 5, 6. And let's see if we can come up with a pattern before we check all 5. Here I added 1, here I added 2, here I added 3. Take a guess. What do you think's next? If you guess 10, let's check our conjecture and see if we're right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we notice a pattern, and we use that pattern to come up with some kind of general rule. We're using inductive reasoning. We have no way of knowing if our conjecture is true, but we have a good sense of feeling about whether it's true or not. When it comes to a conjecture, proving that it's true is very hard, because to prove that something is true, it has to be true no matter what. But disproving something is pretty easy. If we want to show that a conjecture is false, all we need to do is find one counterexample. So a simple conjecture to prove is false is if an angle is not obtuse, then the angle is acute. So notice this conjecture. It supposes you have an angle and you know it's not obtuse, therefore it has to be acute. Well, that's not true. Because here's an angle that's not obtuse and it's not acute. So we can now say this is false. And we know it's false because we have a counterexample for it. Good. If a triangle has two congruent angles, then that triangle has two congruent sides. Now that is a true conjecture. And to show that it's true, well, that's why we're starting this lesson in reasoning and proof. Because to show that this is true for every triangle, no matter what triangle it is, if we know it has two congruent angles, then it has two congruent sides, there's a lot to that. I'll walk you through it shortly. Draw any two angles, this is congruent to that. Well, you can drop what's called an altitude here. And then we know because it's an altitude that that is a right angle. Because that's a right angle, I know it's congruent to that right angle. This side is the same as itself. And then we have this situation where I know these two small triangles are congruent. So this side here has to be congruent to that side here because the two small triangles are congruent. Now I went super fast and I don't expect you to be able to understand or recreate that idea. And there's a lot to do there. But the fact is it is a perfectly valid reasoning that we are going to be studying in geometry. If you take a look at the last conjecture I wrote it in a specific kind of form. It's called an if-then form, or to be more precise, a conditional statement. A conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. If we write it in the if-then form, the part following the if is the hypothesis, the part following the then is the conclusion, and notice that the hypothesis and the conclusion do not include the words if or then. So, this is an important idea in geometry that we will study all year. Not this statement, but if-then statements. Take this one for an example. If it is raining, then there are clouds in the sky. Now, breaking down, what is the hypothesis and what is the conclusion? Hypothesis, it is raining. Conclusion, there are clouds in the sky. There's lots of different ways these conditional statements can be written, but we always want to try to break them down in if-then form. Pause this video and see if you can write these two statements in if-then form. Alright, if you're back, all birds have feathers. If an animal is a bird, then it has feathers. So notice we have an animal is a bird, that's the hypothesis. We have it has feathers, or the animal has feathers, is the conclusion. A lot of times we say if P, then Q. P is the hypothesis, in this case the animal is a bird. Q is the conclusion, in this case the animal has feathers. Two angles are supplementary if they are a linear pair. This one we just have to reverse. If two angles are a linear pair, then the two angles are supplementary. If two angles are a linear pair, then they're supplementary. Good? We want to be able to identify the if-then parts of conditionals because conditional statements have different forms. So we have a conditional statement. We can write the converse by flipping the hypothesis and conclusion. We can write the inverse by negating the hypothesis and conclusion. Or my favorite, we can do the contrapositive, which is we write the converse and then we negate them. So take a look at this example. If the measure of angle A equals 99 degrees, then angle A is obtuse. That is a true statement. The converse flips the conclusion and the hypothesis. If angle A is obtuse, then measure of angle A is 99. That is not true. There are many angles that are obtuse that don't measure 99 degrees. The inverse is negating the hypothesis and the conclusion. Notice the negation of is obtuse is not is acute, it's is not obtuse. The negation of equals is not equal. If the measure of angle A does not equal 99, then it is not obtuse. Again, that's false. We could think of lots of angles that don't measure 99 degrees but are obtuse. Lastly, my favorite, the contrapositive. Flip the hypothesis and conclusion, then negate them both. If an angle is not obtuse, then the measure of the angle does not equal 99. That is a true statement. And what is always true when we deal with conditional statements, that if the contrapositive is true, then the original statement is true. And that the converse and the inverse will also have the same truth value. Meaning if this is true, then the inverse is true. Because take a look. These are contrapositives of each other. Is obtuse equals 99, is not 99, is not obtuse. Anyway, memorize these definitions and be able to follow them symbolically. So we have this one, if P, then Q. The converse, if Q, then P. The inverse, not P means not Q. So I introduced some notation here. The arrow is an if-then. This little tilde is a not, a negation. And then the contrapositive, not Q, means or implies not P. All right, moving on. Take a statement here, write it in if-then form, then write the converse, the inverse, and the contrapositive, and try to figure out if each one is true. The statement, guitar players are musicians. Kian, pick this one for you. So pause the video and try this one. All right, first writing the statement in if-then form. If, I don't want to say if you, but if a person is a guitar player, then the person is a musician. And I'm abbreviating just because I'm running out of space. So, hypothesis, a person is a guitar player. Conclusion, the person is a musician. The inverse. The inverse would be if the person is a musician, then the person is a guitar player. Now that's false. That's false because you could be a musician and not a guitar player. You could be a piano player, a violin player, a drummer, lots of things. The converse, if someone is not a guitar player, then the person is not a musician. And that would be not P means not Q. Again, that statement is false. If you are not a guitar player, then you are not a musician. Well, I'm not a guitar player, and I'm not a musician, but a counterexample would be Nelson. Nelson plays the violin, so he's not a guitar player necessarily, but he is a musician. And then lastly, the contrapositive. The contrapositive says not Q means not P. So that would say if a person is not a musician, then the person is not a guitar player. There is no person that is not a musician and is a guitar player, because if you're a guitar player, then you're a musician. Does that make sense? This has the same truth value, true, as this original conditional statement. I am going to suppose that all guitar players are musicians. Maybe you disagree with that, but I think you're wrong. The last part of this lesson is to start looking at some of our definitions in geometry and thinking of them as conditional statements. So most statements that we want in an if-then form, and I'll tell you why as we continue to work throughout the course. But for a definition, what's cool is any valid definition is true as an if-then, and the converse is also true. So that's what that says up here, that you can write a definition as a conditional statement or as its converse, and they're both true. So take an example of the definition of perpendicular lines. If two lines intersect to form a right angle, then they're perpendicular lines. We can also say if two lines are perpendicular, then they intersect to form a right angle. So Nelson was paying attention when we saw this earlier. If you have a statement that works as a if P then Q, and it works as a if Q then P, you can think of that as a two-way arrow. P goes to Q, but Q also goes to P, so you can write it this way. And the way we write that mathematically is to then say if and only if. If we look at that last statement, if two lines are perpendicular, then they form a right angle. If two lines form a right angle, then they're perpendicular. We can say it this way: two lines are perpendicular if and only if the two lines form a right angle. That is the appropriate way to write a definition, and that's of the phrase, and that's any definition. Any valid definition can be written as a biconditional statement. If you have two lines that are perpendicular, then you know they form a right angle. If you have two lines that form a right angle, then you know those two lines are perpendicular. That's a lot of information, a lot of vocab, but it should give you enough to start on the classwork. The classwork is due Thursday, not at the end of class, but you will also have a video to watch for Thursday's class. All right, have a good day. Peace.